video, we're going to be learning how to use the TI-84 graphing calculator to find the rational roots of a polynomial equation. So you are going to need your graphing calculator, and you'll need a piece of paper to take notes, and you'll need a pencil or pen. At this time, I do want you to pause the video, get your materials, and also please copy down the polynomial that you see on the row that starts with y2. So I want you to copy down this polynomial and then put an equal to 0 at the end of it. When you're done, you can start the video again. Okay, now this equation, it's not written with the equal to 0, so I need you to just remember that there's really an equal to 0 at the end. So if we want to solve this, the thing is that it's a fourth degree polynomial. So this is not something that we can factor. And we could use the rational root theorem to identify some potential rational roots and substitute them in and see if any of those are roots. But because there would be many different possibilities to plug in, we're going to use the calculator. So in order to figure out the rational roots using the calculator, we can use several different strategies. One of them would be using the table, and another would be to use the calculate menu. Now, before we go into that, if you look at this equation, because it is a fourth degree, in order for us in this course to be able to solve it, we need to depress it down to a quadratic, which means we are going to need two rational roots to get it down to a quadratic. So the easiest thing to do to start is to go into your table. So to go into your table, you're going to press second graph. And just make sure, if you haven't already typed this exactly into your calculator, please go ahead and type it in. I would recommend putting the 0 first, and I will explain what that means in a moment. But I would put the 0 first, and then I would put the polynomial. So when you've typed that into your calculator, you'll press second graph. Okay, a table of values will come up. You can ignore the y1. We're really needing to look at the y2 because that's where our polynomial is. So the way that we know that something is a 0 of a polynomial is if the y coordinate is 0. So you'll notice here the point 1, 0 is on the graph of our polynomial. So that means it's an x-intercept. So if it's an x-intercept, it's a 0 of our polynomial function, which means it's going to be a root of our equation when we set it equal to 0. So on your paper, please write down that x equals 1 is one of the roots of the equation. Now you can scroll up and down through the table, but you're unfortunately not going to find any more roots. The thing is though, like I said before, we do need another root in order to be able to solve this. So we're going to have to move beyond the table. Now, you could change the interval of the x-axis, but we don't know what the actual root is going to look like, so it would be hard. We'd have to keep trying out different intervals in order to potentially find it. So that's kind of time consuming, so the strategy I'm going to show you now is more efficient. Okay, so let's go back to y equals. So the reason that I put y equals 0 in one row and then the polynomial in another row is I want to find where they intersect. Now, to be clear, there is an option in the calculate menu that says 0, and you can use that absolutely to find the zeros of a polynomial. However, I have found that this strategy that I'm going to show you is just a little bit easier. If you're familiar with using the 0 function on the calculator, that's totally fine, but I'm going to show you something that I personally think is a little bit less confusing. So y equals 0 is just the x-axis. So we're looking for where our polynomial intersects with the x-axis. Now, the reason that I put the 0 first has to do with when we're finding the intersection points, having the y equals 0 as the first curve makes it a little bit easier. I'll try to explain when we get to that point, but just trust me on this one, okay? So once you have everything nicely written on your paper, typed into your calculator, we're now going to go into the Calculate menu. So the Calculate menu can be accessed by pressing second trace because Calculate is in blue, so we're going to press the blue second button, and then we're going to press trace. So as you can see, number 2 is 0, and again, if that's something that you're comfortable using, that's fine, but I'm going to use intersect. So we're going to press number 5. Okay, when we do this, it says first curve. So it's basically just the cursor is on the first curve, which is the x-axis, the line y equals 0. So you can just press enter. It's not really anything for you to think about. And then it will jump to the second curve. So you just press enter again. And then you can press enter through the guess. And then it gives you the point of intersection. Now, don't mind this number, which is in scientific notation. It's essentially 0. It's a really, really, really tiny number, so it's essentially 0. Okay, so this is one of the points of intersection, which means it's one of the zeros or the x-intercepts of the polynomial. Now, this looks to me like it's probably irrational, but we don't really know because the calculator cuts the decimal off. So there is a way for us to check to see if this is rational. Any number that's rational can be written as a fraction with an integer in the numerator and denominator. So if we can convert this to a fraction, then it's rational. So then we're good to go. So the way that we test this is we're going to use the math fraction enter function on the calculator. But you don't actually have to retype this in, and I don't want you to, because if you type it in, there might be more digits that you're missing. So if you go to the regular original screen of the calculator, and you just press X, which is to the right of the alpha key, this X actually has that value that we just found stored into it. And if you just press from there, you can press enter, but you don't need to. If you press math, enter for fraction, and enter again, it's going to attempt to convert it to a fraction. So it wasn't able to. There are some rare cases where it is possible to convert to a fraction, but the calculator won't do it. However, for all the examples that I give you, if it doesn't convert, it's going to be irrational. Okay, so this is not going to help us because if we use this to depress our equation, it's not even an exact value. If it's irrational, it must mean that the radical was approximated. So this is not helpful to us. So we're going to go back to the graph and we're going to use the calculate menu again and try for another x-intercept. So I like to just look at the graph before I do anything. So we just found this x-intercept all the way to the right. In the table, we found the 1, so we already know that that's there. So there's 2 other ones for us to identify. So we're going to go to second, trace again, and press number 5. However, don't press enter, enter, enter yet because it's going to just return the same x-intercept. So if you use your left arrow key, it'll move you along the x-axis, which is much easier than moving along the red curvy polynomial, which is why I wanted 0 to be in y1. So if you move along the x-axis, you can get close to the next point of intersection that we're going to try. So now once you're pretty close, press enter, enter, enter. Okay. So now, once again, they gave us a decimal that we don't really know if it's rational or irrational. So we're going to test it out by going to second, quit, and just going back to the home screen. Pressing X, because now this new value is stored for X. And then going to math, enter, enter. Okay, so once again, it wasn't able to convert it into a fraction. So we do need another rational root, and there has to be one, because if we have a total of 4 x-intercepts, and we have 2 roots that are irrational, we can't have just one other one that's irrational. So it must be that the root that's all the way to the left, that must be the other rational root. Because remember, irrationals come in pairs. You can't just have one. So if I know that x equals 1 is rational, there has to be another one. Okay, so let's repeat the process. So we're going to do second, trace, number 5. Remember, don't press enter, enter, enter yet. Let's left arrow over to the x-intercept that we're interested in. And now press enter, enter, enter. Okay. Now, you should recognize that this is a repeating decimal, which means it's rational, but we do want to have it in fraction form in order to use synthetic division. We don't want to be using an approximation. So if you know what that fraction is, that's great, but I'm going to show you again how to use the calculator to get it. So I'm going to second quit out of this screen, and then I'm going to press X, math, enter, enter, and then the x-intercept is at -4/3. So now we have used the graph to help us find two rational roots. We know that there's two other roots, and we know that they're going to be irrational because we already tried to convert them. So we don't want to use the decimal approximations, remember, we want the exact roots. So now I'm going to transition over to my iPad, and I'm going to show you how to take those two roots and use them to depress the equation down to a quadratic and then solve the quadratic for the exact irrational roots. The same procedure would be used if the other roots were imaginary. Okay, so just hang tight, I'll be right back. So at this point, we have our two rational roots, and we're going to use them to depress the original equation using synthetic division. So I'm going to use x equals 1 first. It doesn't matter, but sometimes I like to use the easier one first because then the depressed equation, which is a little bit shorter, I'd rather use the fraction on that one. So I'm going to put my 1 outside the little house. Okay, I'm going to write my coefficients, make sure that none of the terms are missing, which they're not. Be very meticulous with all your signs. Okay, so remember we start by dropping down the first number. Okay, then you multiply, so 1 times 3 is 3. And then you add going straight down. So now you get -14. Then you multiply the 1 and the 14, so you get -14. 11 minus 14 is -3. 1 times -3 is -3. 31 minus 3 is 28. And then 1 times 28 is 28. And when we add straight down, we get a 0, which means that we were correct that 1 is a root and that x minus 1 is a factor of the polynomial. So now we're going to use our depressed equation, which technically is now an x to the third equation. So we're going to use that, and we're going to use the root x equals -4/3 to depress it once again. So you can make a whole new box if you want, or I'm just going to add on to this one. Okay, so we have -4/3. Drop down the 3. Okay, now don't get nervous about multiplying these because if you think about it, 4/3 times 3, the 3's are just going to divide out, so you're left with -4. Oftentimes with these synthetic division problems, the multiplication by fractions is really not as bad as it may seem. So you add straight down, so you have -18. Okay, then we have -4/3, I'm just going to show you on the side, times -18. So notice that 3 goes into itself once, it goes into 18 6 times. So now it's just negative 4 times negative 6, which is positive 24. Okay, add straight down, you get 21. Okay, again, now we have negative 4/3 times 21. 3 goes into itself once, 3 goes into 21 7 times. So you're left with negative 28, which is perfect because when you add 28 and negative 28, the sum is 0. Okay, which means that negative 4/3 is a root. Okay, so now we have this depressed equation. Now we don't have to do this next piece, but I do like to do it. I want to now go back and rewrite this polynomial equation in fully factored form based on what we have so far. So x equals 1 as a factor would be written as x minus 1. And then x equals negative 4/3 would be x plus 4/3. There are things that we could do to make it so that it's not a fraction in there, but we're just going to leave it. It's not important at this time. So I'm going to write x minus 1 in parentheses, x plus 4/3 in parentheses, and then I'm going to bring down basically my depressed equation, and because we divided twice, this is now an x squared. Okay, so I'm going to write that. So it's 3x squared minus 18x plus 21 is equal to 0. Okay, so this is equivalent now to the original. You'll notice, and this is something that you should look for, you'll notice that in this last factor, there is a GCF of 3. So I recommend factoring that out to make it easier to solve. So when I factor it out, I'm just going to put the 3 in the front. So now I have 3 times x minus 1 times x plus 4/3. So now I would have x squared minus 6x plus 7 is equal to 0. And just so you know, what I was saying before about the fraction here, see if we multiplied 3 by x plus 4/3, that would eliminate the fraction. But I'm just going to leave it, it's not important. Okay, now we factored as much as possible. You might think that you can factor this last piece, but it's not going to work because you need two numbers that add to negative 6 and multiply to positive 7. So it would only be either 1 and 7 or negative 1 and negative 7, and neither of them add to negative 6. So I'm going to make a t-chart. Now this 3, if you try to set it equal to 0, obviously it doesn't equal 0, so that's just going to drop out. Has nothing to do with the roots. X minus 1 equals 0, so x is equal to 1. X plus 4/3 equals 0, so x is equal to negative 4/3, which we already knew, but I'm just trying to show you how the factorization relates to the roots. Okay, but now this guy we have a problem because it's not factorable. So we have to do something. We can't use the square root method since there's an x in the middle. So we have two choices. Either we can complete the square or we can use the quadratic formula. I'm going to do it both ways to refresh your memory. So I'll actually just do it down here. First I'll do completing the square and then I'll do the quadratic formula. So I'm just going to grab this. Set it equal to 0. Okay, now when you're completing the square, you need the constant to be on the other side. So I'm going to rewrite this, but I'm going to make it equal to negative 7. So it's x squared minus 6x, and I'm just going to leave a space, equals negative 7. So when you're completing the square, you need a number to be added to both sides to make what's called a perfect square trinomial on the left. And the way that you get that number is you take the b term, which is negative 6, you cut it in half, which gives you negative 3, and then you square it. So that would be 9. So you're just taking the b term, cutting it in half, and squaring it. And you're adding that to both sides. If the leading coefficient was not 1, it would be more complicated. We're not going to go into that at this time. Okay, now the reason that we did that is we can easily factor the left-hand side into a binomial squared. It factors into x minus 3 squared. The trick is once you've created this perfect square trinomial, it's just going to be x, bring down whatever sign this is, and cut this in half. And that's how you get your binomial. Or you can just factor it as usual. So then that's equal to 2. Okay, so now we have something squared is equal to a number. So we can now square root both sides. Okay, so on the left, the squared and the square root cancel each other out, so we have x minus 3. And on the right, remember you need to put a plus minus before the radical 2. And then lastly, you just move the 3 over, so finally your answers are x equals 3 plus or minus radical 2. So that's 2 irrational roots. And after I do the quadratic formula, we're just going to check them against the decimals that we got in the calculator. Okay, so now the quadratic formula. If you don't remember what it is, it's posted on Canvas. You can also Google it very easily, but you do need to commit it to your memory for this class. So with the quadratic formula, we need to identify an a, b, and a c. So we need our equation to be set equal to 0. Okay, and then we're going to identify a, b, and c. So a is just the coefficient of x squared, so it's 1. B is the coefficient of x, so it's negative 6. And c is the constant, so it's 7. Okay, and then the formula is just x equals negative b, so in this case it would become a positive 6, plus or minus the square root of b squared. Now make sure you put that b in parentheses because it's a negative, and if you don't put it in parentheses, technically that would give you a negative 36, which is inaccurate. So it's b squared minus 4 times a times c all over 2a. Okay, so then we're going to simplify. So we have x equals 6 plus or minus, so I'll deal with the radical in a second, and it's over 2. So what we have is we have 36 under the radical minus 28. So that's going to just give you 8. Okay, now remember at this point you have to simplify the radical 8. Okay, so radical 8, I'll do this on the side. Again, this is something that hopefully you remember from previous courses, but if not, you can Google it or you look on YouTube for a video. So radical 8 can be rewritten as radical 4 times radical 2. And the 4 is a perfect square, which is why it's beneficial to us. So then instead of writing radical 4, you can just write 2 and bring down the radical 2. Okay, so it's just 2 radical 2. So I'm just going to rewrite this now with my 2 radical 2. And then there's one final step. So it might not always be possible, but it is in this case. You're going to take the denominator, and divide it by each term of the numerator. So you would get, so 6 over 2 is 3. Bring down the plus minus, and then you can only divide the coefficient of the radical by the denominator. You can't divide the denominator into the radicand. That's a no-no. So it's just going to be 1 radical 2 or just regular plain old radical 2. So then that's simplified. Sometimes it won't divide in and you can just leave it. You know, it's not always going to be this nice and neat. Okay, so now we have these two roots. And in order to check that they're equivalent to the roots that we found on the calculator, what I did is I put these into my calculator and I screenshot it so I don't have to go over to my computer. So I'm just going to show you. So these are our intersections. These are irrational intersections. And what I did is I put what we got algebraically, 3 plus radical 2, into the calculator and I got the decimal. Okay, that matches one of our irrational roots, so that's good. And then I put the other one in and I got 1.5857, etc. And then that matches the other irrational root. So while this wouldn't be helpful for imaginary roots, when they're irrational, you can 100% use this strategy to check because there's a lot of room for error. So you want to always check your answers as much as possible to make sure that they're reasonable. Okay, now lastly, I'm just going to write all of the solutions in braces. So we had, it doesn't matter the order really. I'll put the -4/3 first. Then I'll put the 1, and then you can just leave the 3 plus or minus rad 2 the way it is. You can separate it, but it's not really necessary. And then again, checking for reasonableness, there are 4 roots, and that makes sense because the original degree is a 4th degree. So that makes perfect sense. Now, before we conclude, I just wanted to state something about the completing the square versus quadratic formula. If you notice, it actually is easier for this one to complete the square. There's less calculations, so less room for error. It's a little bit faster. I usually use completing the square when the leading coefficient is 1 and when the b term is even, because that's the term that you have to cut in half. So it's a little messier when it's an odd. So whenever the quadratic has a 1 in the front and the b is even, I would do completing the square. And then when it's anything more complicated, I would do quadratic formula. And then remember from other examples that we did in class, if you have something like x squared equals 2, that's super easy because you just have to take the square root, and then it becomes x equals plus or minus radical 2. So that's the other strategy, but that only works if you don't have that middle term. Okay, so thank you for tuning in. If you feel like you need more practice with the graphing calculator, then please feel free to watch the video. The steps for completing the square and for the quadratic formula are posted on Canvas. The graphing calculator steps are posted on Canvas and you have a handout of them. And the synthetic division, a refresher on that, is posted on Canvas. So if there's anything that you're feeling that you don't understand 100%, please take the time tonight to review it because tomorrow in class we're going to apply these ideas to other examples. So thank you for tuning in. Please make sure to submit your notes to Canvas so you get credit for doing the assignment. Have a good night.